On a clear night in October 1995, two Swiss astronomers named Michel Mayer and Didier Queloz were studying the light from a star called 51 Pegasi, a sun-like star about 50 light-years from Earth in the constellation Pegasus. They were looking for the tiny rhythmic wobble that a planet would cause in a star's spectrum as the planet's gravity tugged the star first toward Earth and then away from it, compressing and stretching the wavelengths of light slightly in a cycle matching the planet's orbital period. They found a wobble. It repeated every 4.23 days. This meant a planet was orbiting 51 Pegasi once every 23 days, at a distance of only about 8 million kilometers from the star, less than a fifth of the distance between Mercury and our Sun. Nothing in our solar system prepared astronomers for this. All the gas giant planets in our solar system are far from the Sun, where the material to build them was cold enough to condense. The prevailing theory said that gas giants had to form far from their star and stay there, but 51 Pegasi b was a gas giant, roughly half the mass of Jupiter, orbiting so close to its star that its surface temperature was about 1,000 degrees Celsius, and it completed a full year in just over 4 days. The discovery was shocking enough that Mayer and Queloz's paper was initially met with skepticism, but other astronomers quickly confirmed it. The first exoplanet around a sun-like star had been found, and it was nothing like anyone had expected. Mayer and Queloz received the Nobel Prize in Physics in 2019 for this discovery. That single detection broke open a door that has never been closed again. In the 30 years since 51 Pegasi b, astronomers have confirmed more than 5,700 exoplanets, with thousands more candidates awaiting confirmation. We now know that planets are not a rare luxury, but a fundamental feature of stars. Most stars have planets. In the Milky Way alone, there are estimated to be more planets than there are stars. And the diversity of these worlds, the range of sizes and compositions and orbits and temperatures, is far greater than anything our solar system alone would have led us to imagine. Tonight, we explore planets, not just our own solar system's 8, though we will spend time with each of them, but the full, extraordinary, mind-expanding range of planetary worlds that exist throughout the galaxy. Worlds of iron rain and glass wind, worlds of global magma oceans, worlds where a year lasts only hours, worlds where it rains rubies, worlds that may have oceans hundreds of kilometers deep, and worlds that drift alone through interstellar space with no star to orbit, warmed only by the remnant heat of their formation. Every fact I am going to tell you is real. Every planet I will describe actually exists. The universe has built worlds of extraordinary variety, and tonight they are all yours to carry into sleep. Take a slow, full breath in. Let your chest rise and your lungs expand. Hold it gently. And breathe out long and slow, feeling your body settle completely. Let the weight of your body press gently into the surface beneath you. Let your thoughts quiet. You are on a planet. A warm, living, oxygen-rich, magnetically protected, moon-stabilized planet. And we are going to spend the night exploring what planets and all their diversity truly are. Let us begin with what a planet is. What makes something a planet rather than a star, a moon, an asteroid, or a comet? A planet forms in the disk of material that surrounds a newborn star. In the inner part of the disk, Where temperatures are high, only materials with high melting points can condense into solid particles. Rock-forming minerals like silicates and metal oxides condense first. Iron and nickel condense. These materials clump together, first by electrostatic attraction, then by gravity, building up through billions of collisions into rocky bodies of increasing size, eventually forming rocky planets like Mercury, Venus, Earth, and Mars. In the outer part of the disk, where temperatures are low enough for water ice, methane ice, ammonia ice, and other volatile compounds to condense, there is much more solid material available. A rocky core grows there as in the inner system, but much faster and to a larger size, because there is more material. When the core reaches a critical mass, somewhere around 5 to 15 Earth masses, it begins to gravitationally capture the hydrogen and helium gas of the disk directly, growing rapidly into a gas giant. The gas accretion phase is fast, lasting only a few million years before the star's radiation blows away the remaining gas. If a planet's core reaches critical size before the gas is blown away, it becomes a giant. If not, it remains a smaller rocky or icy body. The process of accretion heats the growing planet enormously through the energy of countless collisions. In the early stages, planets may have global magma oceans on their surfaces, entirely molten, glowing with heat. As the planet cools, denser materials sink to the center, forming a core, while lighter materials rise to form the mantle and crust. This process, called differentiation, is why Earth has a dense iron core and a lighter rocky mantle and crust. Every rocky planet in our solar system went through differentiation early in its history. Now let us think about the remarkable diversity of exoplanets that astronomers have found. The categories are extraordinary. Hot Jupiters are gas giant planets orbiting extremely close to their host stars. 51 Pegasi b was the first confirmed, but hundreds have been found since. They orbit at distances that in our solar system would place them inside the orbit of Mercury. Their surfaces, if they had solid surfaces, would be at temperatures of hundreds to over 1,000 degrees Celsius. They are tidally locked to their stars, the same face always pointing toward the star, creating a permanent day side of extreme heat and a permanent night side of somewhat lesser heat, with ferocious winds circulating heat from the day side to the night side at speeds of thousands of kilometers per hour. HD 1T9733b is a hot Jupiter that has been studied in extraordinary detail. It orbits its star at a distance of only about 4.5 million kilometers and has a surface temperature on its day side of about 1,200 degrees Celsius. But what makes it truly memorable is its atmosphere. The Hubble Space Telescope detected silicate particles in its atmosphere, similar to the material that makes glass on Earth. At HD 189733b's temperatures and pressures, these particles condense into tiny crystalline grains and are swept around by the enormous wind speeds. On HD 189733b, it rains glass. Not liquid glass falling slowly, but tiny glass crystals moving at 8,700 kilometers per hour in winds that encircle the planet. It is one of the most hostile environments ever characterized by astronomy, and it is a planet that actually exists 64 light years from where you are lying. WASP 76b is another extraordinary hot Jupiter. Its dayside temperature is so extreme, about 2,400 degrees Celsius, that iron vaporizes in the atmosphere. The iron vapor is carried by the fierce day-to-night winds to the cooler night side, where it condenses back into liquid and falls as iron rain. The evening terminator of this planet, the boundary between the day and night sides, where the wind carries the iron vapor into the cooler night-side atmosphere, is where iron rains from the sky. It is a world where metal precipitation is part of the weather system. Super-Earths are a category of planets between roughly 1, 5, and 2 Earth radii in size, more massive than Earth but smaller than the ice giants Uranus and Neptune. They are the most common type of planet in the galaxy, yet our solar system has none. They may be rocky, water-rich, or have thick hydrogen atmospheres depending on their formation history and distance from their star. Some super-Earths that orbit in the habitable zone of their star might be ocean worlds, their surfaces covered entirely by water, hundreds of kilometers deep, with no exposed rock anywhere. The water at the bottom of such a deep ocean would be compressed by the weight above it into exotic forms of high-pressure ice, even though the temperature might be hundreds of degrees above the surface temperature of Earth's ocean floors. Cancri E is a super-Earth orbiting so close to its star, 55 Cancri, that it completes one orbit in only 17.7 hours. Its year is less than 1 Earth day long. Its surface temperature is about 2,400 degrees Celsius on the day side. The Spitzer Space Telescope detected a large variation in temperature between the day and night sides, suggesting the planet does not efficiently redistribute heat, which in turn suggests it may have a very thin or patchy atmosphere, or possibly a largely molten surface. There is speculation that this planet, with its extreme heat and its carbon-rich host star, might have a surface of graphite and diamond in some regions, making it potentially the largest known diamond in the galaxy. This remains highly speculative, but it is a real hypothesis based on real data. Mini-Neptunes, or sub-Neptunes, are planets between roughly 2 and 4 Earth radii, which appear to have extended gaseous envelopes of hydrogen and helium surrounding rocky or water-rich cores. They are extremely common in the galaxy. They are so abundant that the Kepler Space Telescope found them around a significant fraction of the stars it observed. We do not have one in our solar system. Their atmospheres are thought to be hostile to life as we know it. Ocean worlds are planets thought to be composed primarily of water, with global oceans hundreds or even thousands of kilometers deep. Some exoplanets detected by Kepler and other missions are in the right size and density range to be ocean worlds. Our own solar system's moons Europa, Ganymede, and Callisto, and Titan and Enceladus at Saturn are ocean worlds in a sense, but smaller and surrounded by ice. A true ocean world planet orbiting a star would be a planet of water from pole to pole, with perhaps clouds of water vapor above and strange high-pressure ices at the bottom of the ocean where it meets whatever rocky core lies beneath. Let your breath settle even more slowly now. Out there, across the galaxy, all these worlds exist: glass rain and iron rain, and water worlds and lava worlds. And here you are, on a rocky world with liquid water and an oxygen atmosphere and a magnetic field and a moon, a world of extraordinary calibration. Now let us spend time with each of the planets in our own solar system, because each one, when you look at it closely, is worthy of a long, quiet night of reflection. Mercury, the smallest and innermost planet. Airless, geologically ancient, covered in craters from billions of years of meteorite impacts, its surface simultaneously baking under the nearby sun and freezing in the long dark of its nights. Mercury has a surprisingly large iron core for its size, comprising about 83% of the planet's radius. Scientists suspect this is because Mercury may have suffered a giant impact early in its history that stripped away much of its outer rock, leaving the dense iron interior disproportionately dominant. Mercury's surface, seen up close in images from the Messenger spacecraft, is scarred and ancient, covered in a fine gray dust called regolith, with impact craters of all sizes overlapping and intersecting, recording billions of years of bombardment by the debris of the early solar system. One of Mercury's most remarkable features is its wrinkle ridges, long sinuous scarps that wind across the surface for hundreds of kilometers. These form as Mercury's interior cools and contracts, causing the crust to buckle and thrust upward along faults. Mercury is shrinking. Its diameter has decreased by perhaps 7 kilometers over billions of years as it slowly loses heat. The wrinkle ridges are the visible signs of this long, slow contraction. Venus, the evening star and the morning star, the brightest natural object in Earth's sky after the sun and moon, the planet named for the goddess of love and beauty, which turns out to be the most hostile planetary surface in the solar system. Venus rotates so slowly that a Venusian day is longer than a Venusian year. The sun rises in the west and sets in the east. The dayside and nightside temperatures are essentially equal because the thick atmosphere distributes heat so efficiently, and the sulfuric acid clouds that circle the planet every 4 days in ferocious super-rotation winds create a sky that is never clear, never blue, always orange and overcast. The surface of Venus is a landscape of volcanic plains, mountains, and exotic geological features. Ishtar Terra is a highland region comparable in size to Australia, with Maxwell Montes at its eastern end, the highest mountains on Venus, rising about 11 kilometers above the mean planetary radius. The tops of the Maxwell Montes are covered in what appears to be a bright metallic frost, not water ice as on Earth's mountains, but metallic compounds of lead sulfide and bismuth sulfide that condense as vapor in the lower, hotter regions and precipitate out at the cooler, higher altitudes. Mountains frosted with metal rather than snow. The Soviet Venera landers that reached the surface of Venus between 1970 and 1985 are among the most extraordinary achievements of planetary exploration. Each lander had to survive entry into the atmosphere, descend through 50 kilometers of sulfuric acid clouds, and then operate on a surface where the pressure is 92 times Earth's atmospheric pressure and the temperature is hot enough to melt lead. The Venera 13 lander, which reached the surface in March 1982, survived for 127 minutes before being destroyed. It photographed the Venusian surface, showing a flat landscape of angular slabs of dark volcanic rock under an orange sky, the orange color resulting from the filtering of sunlight through the dense clouds. In 127 minutes on the surface of Venus, Venera 13 transmitted the first color images of another planet's surface landscape, Earth, the third planet. the one you are on. Seen from space, a sphere of vivid blue and white and brown and green, the only planet in the solar system with liquid water covering most of its surface, the only one with continents of exposed rock rising above a global ocean, the only one with green plants on land and plankton in the sea producing oxygen continuously, the only one with that extraordinary thin blue line of atmosphere around its rim that astronauts find so striking when they see it from orbit. Earth's ocean covers about 71% of the surface. Its deepest point, the Challenger Deep, is nearly 11 kilometers below the surface. Its average depth is about 3.7 kilometers. The total volume of the ocean is about 1.335 billion cubic kilometers. If you could pour all of Earth's ocean water onto Mars, you would cover the entire Martian surface to an average depth of about 30 meters. The ocean shapes Earth's climate, distributes heat from the tropics to the poles, moderates temperature extremes, and is the ultimate source of most of the water vapor that forms rain and snow on land. The Moon, Earth's companion, is the fifth largest moon in the solar system and extraordinarily large relative to the planet it orbits. The Moon's diameter is about 27% of Earth's diameter. No other planet in the solar system has a moon so large relative to itself, except arguably Pluto and Charon. The moon's presence stabilizes Earth's axial tilt and creates the tides that have driven coastal evolution and shaped human civilization through their predictable rhythms. The tidal bulge that the moon raises in Earth's oceans is a tangible demonstration of how connected these two bodies are, each one constantly feeling the gravitational presence of the other. Mars, the red planet, the planet that has inspired more science fiction, more exploration missions, and more debate about the possibility of life than any other world. Mars is a geologically complex world with a fascinating history. Its northern hemisphere is dominated by vast, relatively flat lowlands, while the southern hemisphere is older, more heavily cratered, and elevated. The boundary between these two hemispheres, called the hemispheric dichotomy, is one of the most striking features of Mars's global geology, and its origin is still debated. The Tharsis Bulge, a vast volcanic plateau roughly the size of North America, dominates the western hemisphere of Mars. It is home to the Tharsis Montes volcanoes, a line of 3 large shield volcanoes, and Olympus Mons, the largest volcano in the solar system. The loading of the Tharsis Bulge on the Martian crust has deformed the crust extensively, contributing to the formation of Vs Marineris to the east. This canyon system runs along the equator for about 4,000 kilometers, reaching depths of up to 7 kilometers. The canyon is thought to have formed through a combination of tectonic rifting, collapse of the valley floor, and wind erosion over billions of years. Mars currently has 2 operational rover missions on its surface. The Curiosity rover has been driving through Gale Crater since 2012, climbing the sedimentary layers of Mount Sharp at the center of the crater and reading the geological record of an ancient lake environment. It has found complex organic molecules in the ancient rocks, evidence that the chemistry necessary for life was present in the ancient Martian environment. The Perseverance rover has been exploring Jezero Crater since 2021, collecting rock and soil samples for eventual return to Earth. Jezero is an ancient lake crater with a well-preserved river delta at its western edge, one of the most promising locations for finding evidence of ancient microbial life if it ever existed on Mars. Jupiter, the king of planets, the planet that shaped the solar system. Jupiter's enormous gravity has influenced every other object in the solar system since it formed. Early in the solar system's history, Jupiter may have migrated inward from its original formation location and then back outward, scattering the material of the inner solar system and disrupting the formation of larger rocky planets in the habitable zone. This grand tax scenario, as it is called, may explain why Mars is so small compared to Venus and Earth, and why the asteroid belt was depleted. Jupiter is not a passive bystander in the solar system. It is an active gravitational force that has been reshaping the architecture of the system for 4.6 billion years. Jupiter's atmosphere is organized into alternating bands of darker belts and lighter zones that run parallel to its equator. The belts are regions where air is sinking and being compressed and heated. The zones are regions where air is rising. The boundary between belts and zones is where the strongest jet streams blow, with wind speeds of up to 360 kilometers per hour. The entire banded structure rotates with the planet's rapid rotation once every 10 hours, which is why the bands are so starkly parallel. The rapid rotation also creates the equatorial bulge, making Jupiter noticeably flattened at the poles, with a polar diameter about 7% less than its equatorial diameter. Jupiter has a faint ring system discovered by Voyager 1 in 1979. Unlike Saturn's brilliant ice rings, Jupiter's rings are made of fine, dark dust kicked off the surfaces of the inner moons by micrometeorite impacts. They are so thin and dark that they were not discovered by Earth-based observers. 4 distinct ring components have been identified: a thin outermost gossamer ring, a broader main ring, a flat halo ring, and an inner gossamer ring. Together they extend from about 92,000 kilometers to about 226,000 kilometers from Jupiter's center. From inside the rings, looking outward, you would see Jupiter's vast cloud-banded disk above you and scattered faint dust around you. Saturn, the jewel of the solar system. No photograph does justice to the experience of seeing Saturn through a telescope for the first time. Even a small telescope shows the rings clearly and the contrast between the golden ball of the planet and the white. Elegant rings surrounding it at an angle is one of the most beautiful sights in astronomy. Saturn's rings are made of water ice, ranging from tiny dust grains to boulders several meters across, each particle on its own orbit around Saturn, interacting with the other ring particles and with the gravitational influence of Saturn's moons in ways that create the complex structure of gaps, ringlets, waves, and braids visible in the Cassini spacecraft's images. The Cassini division, the prominent dark gap in Saturn's rings visible from Earth, is maintained by a gravitational resonance with the moon Mimas. Particles in the Cassini division orbit Saturn in exactly half the time that Mimas takes to orbit, meaning that they receive a gravitational push from Mimas at the same point in each orbit. This repeated resonant perturbation gradually pushes particles out of the Cassini division, keeping it relatively clear. Similar resonances with other moons maintain other ring gaps, creating the banded structure of the ring system. Saturn's hexagonal polar storm is one of the most geometrically extraordinary structures in the solar system. A persistent six-sided jet stream surrounds Saturn's north pole at about 78 degrees north latitude, forming a hexagonal shape that has remained stable for decades. Each side of the hexagon is about 14,500 kilometers long, larger than Earth's diameter. Inside the hexagon, a central vortex swirls. The hexagonal shape of the jet stream is thought to be maintained by the dynamics of the surrounding atmosphere, producing a stationary geometric wave pattern in the flow. Similar laboratory experiments with rotating fluids have produced polygonal patterns, suggesting that Saturn's hexagon is an example of a more general fluid dynamics phenomenon at work in the atmosphere of a giant planet, Uranus, the ice giant that lies on its side. Most of what we know about Uranus comes from a brief encounter with Voyager 2 in January 1986, a flyby that lasted only a few hours but revealed a world that still defies complete understanding. Uranus is the coldest planet in the solar system, with a minimum atmospheric temperature of minus 224 degrees Celsius, colder even than Neptune despite being closer to the Sun. The reason for this is unknown. Unlike all the other giant planets, Uranus radiates almost no excess heat from its interior. Its interior heat is either very small, which would require an unusual formation history, or is somehow trapped and cannot escape, which would require an unusual atmospheric structure. Uranus has 13 known rings, discovered in 1977 when the planet passed in front of a distant star, and the star briefly dimmed as the rings crossed in front of it before the planet itself caused the main occultation. The rings are narrow, dark, and made of material much darker than the ice one might expect to find in the outer solar system. The rings also have a slight tilt following Uranus's extreme axial tilt, so they appear nearly circular when viewed from certain directions and edge on from others. Neptune, the last of the solar system's 8 planets. The only planet predicted before it was observed. In 1846, 2 mathematicians independently calculated the position of an unknown planet that must be causing the observed perturbations in the orbit of Uranus. The French mathematician Urbain Le Verrier sent his prediction to the Berlin Observatory, and on September 23, 1846, Johann Gottfried Galle and Heinrich Louis de Rest pointed their telescope at the predicted location and found Neptune within 1 degree of where Le Verrier had said it would be. It was the triumph of mathematical physics applied to the solar system, the discovery of a planet by calculation. Neptune is a vivid deep blue in color, the most intensely colored of the solar system's planets in visible light. The color is due to the absorption of red and infrared light by methane in its atmosphere, which leaves the reflected sunlight enriched in blue wavelengths. Neptune has the strongest winds in the solar system, reaching up to about 100 kilometers per hour in some regions of its atmosphere. The source of the energy driving these winds remains incompletely understood, because Neptune receives very little solar energy at its distance from the Sun. Let your breathing slow even more now. The planets are out there in their orbits, each one turning, each one with its own character, its own weather, its own history. Saturn's hexagonal storm is spinning. Neptune's winds are blowing. Jupiter's great red spot is churning. Venus's sulfuric acid clouds are racing around the planet, and Mars's ancient craters are lying still and cold under a thin, pale sky. In the past decade, one of the most exciting developments in planetary science has been the discovery of the TRAPPIST-1 system. TRAPPIST-1 is an ultra-cool red dwarf star about 40 light-years from Earth. In 2016 and 2017, astronomers announced the discovery of 7 Earth-sized planets orbiting this star, 3 of them in the habitable zone where liquid water could potentially exist on their surfaces. This is the largest number of potentially habitable planets ever found around a single star. All 7 planets are rocky and of roughly Earth-like size and mass. Their orbits are very close to the star because TRAPPIST-1 is much smaller and cooler than the Sun, and the habitable zone is correspondingly much closer in. The innermost planets complete their orbits in as little as 1.5 Earth days. The outermost takes about 19 days. The James Webb Space Telescope has been studying the TRAPPIST-1 planets since its first science operations in 2022. Initial observations of TRAPPIST-1b and TRAPPIST-1c have found no evidence of substantial atmospheres on those planets, suggesting they may be bare rocks like Mercury. But the other planets, particularly TRAPPIST-1, F and G in the habitable zone, are harder to study, and their atmospheric status remains uncertain. The potential for liquid water, and thus for life, on the TRAPPIST-1 habitable zone planets continues to drive intense scientific interest. Proxima Centauri b is the closest known exoplanet to Earth, orbiting Proxima Centauri, the nearest star to the Sun, at a distance of only 4.24 light-years. Proxima Centauri b was discovered in 2016 and orbits in the habitable zone of its host star, completing one orbit every 11.2 Earth days. Proxima Centauri is a red dwarf, much smaller and dimmer than the Sun, so its habitable zone is much closer in. The planet receives about the same amount of energy from its star as Earth receives from the Sun, which means liquid water could potentially exist on its surface. However, red dwarf stars are notoriously active, frequently producing powerful flares that blast their nearby planets with intense ultraviolet and X-ray radiation. Proxima Centauri is particularly active, and whether Proxima Centauri b can maintain an atmosphere in the face of the stellar activity is one of the central questions about this planet. Without an atmosphere, there can be no liquid water at the surface. Whether Proxima Centauri b has the right conditions for life is unknown, but it is the nearest exoplanet to Earth, and it continues to fascinate. Rogue planets, also called free floating planets, are a category of worlds that orbit no star. They travel through interstellar space alone, expelled from their original planetary systems by gravitational interactions with other planets or with passing stars. Estimates suggest that the Milky Way may contain billions of rogue planets, possibly outnumbering the planets that orbit stars. They are extraordinarily difficult to detect because they emit no light and have no star nearby to reveal them. Gravitational microlensing, the bending of light from a background star by the gravity of a passing rogue planet, is the main detection method, and several rogue planet candidates have been found this way. A rogue planet would be a dark, cold world, traveling through the interstellar void at typical velocities of tens of kilometers per second relative to the surrounding stars. Without a star's warming, its surface would be at temperatures approaching absolute zero. But some rogue planets might have internal heat from radioactive decay or from formation that could maintain liquid water beneath an ice shell, similar to Europa and Enceladus. A rogue ocean world drifting through the interstellar night, warm inside despite the freezing exterior, is a possibility that some scientists take seriously as a potential home for life. The concept of a habitable zone is one of the most important in planetary science. The habitable zone, sometimes called the Goldilocks zone, is the range of orbital distances from a star where a planet with the right atmospheric composition could maintain liquid water on its surface, not too hot, not too cold, but just right. Earth is in the habitable zone of the Sun. Mars is at the outer edge, and may have had liquid water in its early history when it had a thicker atmosphere. Venus is at the inner edge, and may have had liquid water early in its history before runaway greenhouse warming took hold. But the habitable zone concept has limitations. It assumes a planet needs surface liquid water to be habitable, but Europa and Enceladus have liquid water subsurface oceans far outside the traditional habitable zone. It assumes an Earth-like atmosphere, but different atmospheric compositions could extend or contract the habitable zone significantly. It does not account for the type of star, which can have enormous effects on the habitability of nearby planets through stellar activity and the availability of ultraviolet light for photosynthesis. The true range of environments that could support life is unknown, and the habitable zone is only a first approximation of where to look. The detection of planets around other stars is itself a story of extraordinary ingenuity. The transit method used by the Kepler and test space telescopes detects planets by the tiny dimming of a star's light as a planet passes in front of it. For an Earth-sized planet orbiting a Sun-like star, this dimming is about 0.01%, a decrease in light output of 1 part in 10,000. Kepler measured the brightness of about 150,000 stars continuously for 4 years with enough precision to detect this tiny dimming, finding thousands of planets. TESS, its successor, surveys the brightest and nearest stars with similar precision. The radial velocity method, used by Mayer and Queloz to find 51 Pegasi b, measures the tiny Doppler shift in a star's spectrum as a planet's gravity tugs it back and forth. For Earth orbiting the Sun, the radial velocity signature is about 9 centimeters per second, a speed slower than a slow walk. Measuring this from 150 light years away requires spectrographs of extraordinary precision, and the instruments of the past decade have reached this capability, opening the possibility of detecting Earth-like planets around nearby Sun-like stars. The universe is full of planets, more than there are stars, in many sizes and compositions, and orbital configurations and temperatures. On some of them, conditions may be right for chemistry of extraordinary complexity. On at least one of them, that chemistry produced life that eventually built telescopes and sent radio waves into the sky and launched spacecraft to its neighboring worlds, and detected the tiny wobbles of distant stars and found the planets circling them, and then lay down on that planet and looked up at the night sky and thought about all the other planets out there, shining in the reflected light of their own stars. That is you on your planet tonight, one world among trillions, known, warm, breathing at rest. Before we drift fully into sleep, there are more extraordinary planet facts worth carrying quietly with you. The Kepler Space Telescope, which operated from 2009 to 2018, fundamentally changed our understanding of how common planets are in the galaxy. Kepler was pointed at a single patch of sky in the constellation Cygnus, containing about 150,000 stars, and it watched those stars continuously for 4 years. Its goal was to detect the tiny, repeated dimming of stars as planets crossed in front of them. Over its mission, Kepler discovered or confirmed over 2,600 exoplanets, but its most important contribution was statistical. By studying the fraction of stars with detectable planets in its sample, Kepler allowed astronomers to estimate how many planets there are in the entire galaxy. The answer was extraordinary. Virtually every star has planets, and there are likely more planets in the Milky Way than there are stars. There may be 100 billion planets in our galaxy. There may be more. Kepler 442b is one of the exoplanets most similar to Earth that has been found. It orbits a star about 1,200 light-years away in the constellation Lyra. The star is slightly smaller and cooler than the Sun. Kepler 442b is about 1.34 times Earth's radius, slightly larger than Earth, and orbits in the habitable zone of its star, receiving about 70% of the solar radiation that Earth receives from the Sun. Its orbital period is about 112 Earth days. It is rocky, or at least consistent with a rocky composition, and receives enough light from its star for liquid water to potentially exist on its surface. Of the thousands of exoplanets discovered, Kepler 442b remains one of the most interesting candidates for a world that might have conditions suitable for life. Kepler 22b was the first confirmed exoplanet in the habitable zone of a Sun-like star, announced in 2011. It is about 2.4 times Earth's radius, which puts it in the mini-Neptune category. It is about 600 light-years away. Its orbital period is 290 Earth days, close to an Earth year. The temperature at its surface, if it has a rocky surface and an Earth-like atmosphere, would be about 22 degrees Celsius, which is a comfortable room temperature. If it is a water world, its surface would be a global ocean. The nature of Kepler 22b's surface and atmosphere is unknown because it is too far away and too small relative to its star for current telescopes to characterize. TOI 700 is an Earth-sized planet in the habitable zone of its star, discovered by the TESS telescope in 2020. The star TOI 700 is a red dwarf about 101 light-years from Earth. TOI 700 is about the same size as Earth and orbits in the outer portion of the star's habitable zone. It receives about 86% of the energy that Earth receives from the Sun, which suggests it could maintain liquid water on its surface with the right atmosphere. Further observations have since discovered additional planets in the TOI 700 system, including TOI 700e, another potentially habitable planet slightly smaller than Earth. This system is one of the closest known systems with potentially habitable Earth-sized planets. Brown dwarfs occupy the twilight between planets and stars. They are objects too massive to be planets, but not massive enough to sustain the nuclear fusion of hydrogen in their cores that would make them stars. The boundary between the most massive planets and the least massive brown dwarfs is conventionally set at about 13 Jupiter masses, above which deuterium fusion can briefly occur. Brown dwarfs were long predicted theoretically, but only confirmed observationally in 1995, the same year as the first exoplanet discovery. They are extraordinarily common, possibly as common as stars. The nearest brown dwarf to the Sun is Lumen 16, a pair of brown dwarfs about 6.5 light-years away. Brown dwarfs have atmospheres containing clouds of iron and silicate minerals at different temperature layers, creating a complex vertical structure of different cloud types. In the coolest brown dwarfs, called Y dwarfs, the temperatures are cool enough for water ice clouds and perhaps even ammonia clouds. The atmospheres of planets are extraordinarily diverse and represent one of the most varied aspects of planetary science. Mercury has virtually no atmosphere, only a thin exosphere of atoms sputtered off the surface by solar wind and micrometeorites. The surface pressure is about 5 times 10 to the power of minus 15 bars, a quintillion times thinner than Earth's atmosphere. Venus has an atmosphere 92 times thicker than Earth's, composed almost entirely of carbon dioxide with clouds of sulfuric acid. Earth's atmosphere is 78% nitrogen and 21% oxygen, maintained at its composition by the continuous action of living organisms. Mars has an atmosphere of carbon dioxide about 1% as thick as Earth's, with trace amounts of nitrogen and argon. Jupiter and Saturn have atmospheres of hydrogen and helium, the same 2 lightest elements that make up most of the Sun. Uranus and Neptune have hydrogen-helium atmospheres, but with significant additions of methane and other ices that give them their blue-green colors. Among exoplanets, atmospheric diversity is even greater. Some hot Jupiters have atmospheres containing sodium, potassium, calcium, titanium oxide, and water vapor, all detected through spectroscopy. Some are so hot that their atmospheres are partially evaporated by their star, creating a comet-like tail of escaping gas that trails behind the planet in its orbit. Some super-Earths have thick hydrogen atmospheres, like small versions of Neptune. Some may have atmospheres of carbon dioxide, nitrogen, or even oxygen, though the detection of oxygen in an exoplanet atmosphere would be particularly exciting, as it is potentially a biosignature, a sign of life. Lava planets, or magma ocean planets, are a category of exoplanet whose surfaces are thought to be partially or entirely molten, either because they orbit so close to their star that the intense heat melts the rock, or because they are so young that they have not yet cooled from formation. 55 Cancri E is a candidate. Kepler 10b is another. A rocky planet orbiting so close to its star that its year lasts only 20 hours and its dayside temperature is thought to be hot enough to melt rock. The surface of such a planet would be a glowing, shifting magma ocean with occasional rocky outcrops at the most extreme tidal bulge points, illuminated by the nearby star's harsh light. On lava planets, the concept of weather becomes something extraordinarily alien. Rocks do not simply sit on the surface itself is flowing. Silicate minerals that vaporize at the highest temperatures on the day side are carried by atmospheric circulation to the night side, where they cool and condense, falling as silicate rock rain. The weather cycle is one of rocks evaporating on the sun-blasted day side and raining out on the cooler night side. The concept of seasons, of winter and summer, of rain and drought, all of these familiar frameworks do not apply to a world whose surface is a flowing liquid of molten silicate rock. Let your breathing slow a little more. You are on a solid, cool, beautiful world with water, rain, and snow, and gentle seasons and breathable air. The lava planets are far away, their surfaces glowing and alien. Johannes Kepler, the 17th century German mathematician and astronomer, discovered 3 laws that govern the motion of every planet in the universe around every star. The first law says that every planet orbits its star in an ellipse, not a perfect circle, with the star at one focus of the ellipse. The second law says that a planet moves faster in its orbit when it is closer to its star, and slower when it is farther away, so that a line drawn from the star to the planet sweeps out equal areas in equal times. The third law says that the square of a planet's orbital period is proportional to the cube of its average distance from its star. These 3 laws, derived by Kepler from painstaking analysis of Tycho Brahe's observational data in the early 17th century, describe the orbits of every planet we have ever discovered, in our solar system and around other stars. They are among the most elegant and universal laws in all of science. Newton later showed that Kepler's laws are a consequence of his law of universal gravitation. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Gravity is the architect of planetary systems. It pulls the material of a protoplanetary disk together into planets. It shapes those planets' orbits according to Kepler's laws. It keeps the planets in stable orbits for billions of years. It is the same force pulling you gently but continuously toward the center of the Earth right now. The seasons of planets are a direct expression of the geometry of their orbits and the tilt of their axes. Earth's seasons are caused primarily by axial tilt. Mars, with a similar axial tilt of about 25 degrees, has seasons comparable to Earth's but longer, since a Martian year is about 687 Earth days. Saturn has an axial tilt of about 27 degrees, giving it seasons of about 7 Earth years each. Uranus, with its extreme 97.77 degree tilt, has seasons of about 21 Earth years each, and the polar regions experience the most extreme seasons, with 42 years of continuous sunlight followed by 42 years of polar night. Mercury, with an axial tilt of only 0.034 degrees, essentially has no seasons, and Venus, with an axial tilt of 177 degrees, is technically rotating retrograde, meaning its seasons are driven by its slow retrograde rotation and are almost undetectable against the background of its extreme greenhouse heating. The geology of rocky planets is another area of profound diversity. Earth's surface is continuously renewed by plate tectonics, with new crust forming at spreading ridges and old crust recycling into the mantle at subduction zones. This process recycles carbon and other elements, regulating the carbon cycle and helping maintain a stable climate over geological time. Venus appears not to have plate tectonics in the same form, its surface thought to be a single rigid plate that undergoes periodic catastrophic resurfacing events, in which the heat built up in the interior is released suddenly through global volcanic activity that resurfaces most of the planet every few 100 million years. Mars, with its smaller size and cooled interior, has been geologically inactive for billions of years, its ancient surface preserved in extraordinary detail. Mercury, despite its small size, shows evidence of a history of volcanic activity and ongoing slow contraction. The cratering record on planetary surfaces is a window into the early history of the solar system. Heavily cratered surfaces, like the southern hemisphere of Mars, the highlands of the Moon, and virtually all of Mercury, preserve the record of the late heavy bombardment, a period about 4 billion years ago when the rate of impacts was dramatically elevated, possibly because the giant planets were migrating and disrupting the orbits of asteroids and comets. Lightly cratered surfaces, like Earth's continents, are young in geological terms, continuously reshaped by erosion, tectonics, or volcanism that erases the craters. The exploration of our solar system's planets by spacecraft has been one of the greatest scientific adventures in human history. Mercury has been studied by Mariner 10 in 1974 and 1975, and by the Messenger mission from 2011 to 2015. The Bepi-Colombo mission, a joint ESA and JAXA project launched in 2018, is currently en route to Mercury for orbital insertion in late 2025, promising a decade of new discoveries. Venus has been visited by many Soviet Venera landers and by the Magellan orbiter, and is the target of new missions, NASA's Da Vinci and Veritas, and ESA's Envision, all approved for launch in the 2030s. Mars has been explored by a fleet of orbiters and rovers, Jupiter by Pioneer, Voyager, Galileo, and Juno, Saturn by Pioneer, Voyager, and Cassini, Uranus and Neptune only by Voyager 2. Plans for future missions to Uranus and Neptune are being discussed, with the Uranus orbiter and probe identified as the highest priority large mission in the most recent Planetary Science Decadal Survey. The planets of our solar system were all imaged together for the first time, and a portrait assembled from images taken by Voyager 1 in February 1990 from a distance of about 6 billion kilometers. The family portrait, as it is called, shows 6 of the solar system's planets as tiny dots against the black background of deep space. Earth is the pale blue dot, famously described by Carl Sagan. Jupiter is a slightly brighter point. Venus is a bright crescent. Saturn, Uranus, and Neptune are faint pinpoints. The portrait is humbling in its perspective. All these worlds, each one a complex and extraordinary place, are barely visible as individual pixels from the edge of the solar system, and yet each of these worlds has a history of billions of years. Each has a geology, a weather system, a magnetic field or the memory of one, a set of moons or a ring system or both, a chemistry and a temperature range and an orbital period. Each one, if you could stand on its surface, would be a world of immense variety and detail, as complex and strange and beautiful in its own way as Earth. The night is quiet. The planets are in their orbits. Let everything settle now. The planets in our solar system are turning in their orbits. The exoplanets of TRAPPIST-1 are spinning through their short years. The hot Jupiters are being blasted by their stars. The ocean worlds are keeping their oceans liquid in the dark. The rogue planets are drifting through the cold. And you are here, on this one perfect world, on its surface, warm and still. Sleep now. The planets do not need your attention tonight. They have been managing their orbits for billions of years and will continue for billions more. The universe has given you this planet, this atmosphere, this gravity, this warmth, and this night. You are lying on a rocky planet with a solid iron core and a liquid iron outer core, generating a magnetic field that has been protecting this world for at least 3.5 billion years. You are breathing an atmosphere that took more than 2 billion years of biological activity to oxygenate to its current composition. You are made of atoms that were synthesized in stars that formed and died before the sun existed. The water in your body has been cycling through Earth's systems for nearly 4 billion years. The ground beneath you is crust floating on a slow-moving mantle that has been churning for 4.5 billion years. Every system that sustains you has been running quietly and continuously for longer than you can meaningfully imagine. And somewhere out there, 4,024 light-years away, Proxima Centauri b is orbiting its small red star every 11.2 days, and we do not know if it has an ocean or a sky or a sound that carries through an atmosphere. And 40 light-years away, the 7 worlds of TRAPPIST-1 are spinning through their short years. Some of them perhaps with liquid water on their surfaces, some of them perhaps bare and cold and silent. And 1,200 light-years away, Kepler 442b is completing one orbit every 112 days around its slightly dimmer star, possibly with a surface of rock and water, possibly with a sky. We do not know what those skies look like, if they exist. We do not know what sounds, if any, travel through those atmospheres. We do not know if anything looks up at those skies and wonders about the lights it sees. But you are here, on a planet with a sky, and it is night, and the sky above you is full of the light from other stars, and around many of those stars, planets are moving, quietly, in the dark. Good night.